All right, so we have finished pudding. Now let's get ourselves into some fats, the lipid class of molecules. Now, these don't fall into the monomer-polymer model quite as well, but they do all right. Here, we'll go ahead and title this one. And that is going to be fats, and also known as lipids. So, this category of macromolecules has got a lot of different things in it. And we're going to go through some of them, but not inclusive, but pretty good. All right, so fats generally, not always, but generally, they can be categorized as not being water soluble. Oils, and oil and water don't mix, right? Okay, so oils are a classic kind of fat. And the basic monomer of a fat is a molecule known as a fatty acid. So a fatty acid is, just as the name implies, it's got an acid group on it, but then it has a really long chain carbon stretch. And that's what makes it nonpolar. So the acid part actually makes it a little bit water soluble, but there's such a gigantic train of carbons that it can't be water soluble. And so when you're looking at like a jar or a bottle of olive oil or corn oil, your favorite oil, it is a mix of free fatty acids and then fatty acids that are linked together a bit, and we'll see how that goes. So first off, let's talk about fatty acids. So you may take fatty acid supplements. People that take omega-3 fatty acids or taking fish oil. There are a whole range of fatty acids that people who are on a ketogenic diet take that are sort of a short chain fatty acids that have some abilities to interact with your metabolism a little bit better. But fats are a really good source of calories. There's a lot of energy in a fat, and they actually should be probably the bulk of your calories should come from fats. So lots of different fats and oils, and just to think about this, we're going to get into it. We have some fats like butter or Crisco or margarine, lard, coconut oil that are solid at room temperature and semi-solid anyway. And then we have a lot of fats like olive oil, corn oil, peanut oil, soybean oil, canola oil, blah, 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 that are liquid at room temperature. And we want to look to see what is going on there. So let's think first about a fatty acid. Now, fats and fatty acids and fatty acid biochemistry is actually a really complicated area of biochemistry, quite fascinating, I'm sure. There are a lot of different fatty acid structures floating around. Primarily, though, in humans anyway, or in animals and for most organisms, fatty acids tend to be clustered into very specific kinds of structures. The number one thing is 18 carbon fatty acids. 18 carbon. That is your standard. And there are links of fatty acid chains that just ain't found in living systems. We just don't make them. But 18 carbon, that's your number one fat. So when you're looking at a bit of blubber, you got a lot of 18 carbon fatty acids. Let's draw one here for a second. So to draw an 18 carbon fatty acid, first off, we got to draw 18 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Can you see that one over there? Yeah. Sure. I'll do that. So, an 18 carbon fatty acid. That's a lot of carbons. Now, let's make this into a fatty acid by putting, I like to go on this side, but you can't see it so well, the carboxylic acid on this last carbon. So here is the last carbon. We have the OH group and the double bond oxygen. There's that OH group. Okay, that is an 18 carbon fatty acid. So to draw fatty acid, you put a bunch of carbons out there, and then you put the carboxylic acid group at the back end. And this is a very common fatty acid structure, 18 carbons. And now, you ever heard about omega-3 fatty acids? These are all based on 18 carbon. Now, again, the organic chemistry biz has got so many different names. This is also known as linoleic acid. But we got all these carbons and they got nothing on them. We got to put stuff on them. We have to add hydrogens. Now, what we're going to do is, initially, we're going to put hydrogens. I'm going to just see if I can orient it so you have that last carbon there. We're going to put hydrogens at every possible spot. We're going to saturate this guy with hydrogens. It's going to become a saturated fat. So, let's start putting hydrogens everywhere. Beep, 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 beep. This is tedious and stupid, and I should stop the video. I'm wasting internet bandwidth drawing nothing but hydrogens. But, there you go. Now, when we end up adding hydrogens at every possible spot, we will have made a molecule that is known in the trade, in the biz, as stearic acid. And while it's not quite Halloween, and who knows what Halloween is going to be like in the time of COVID, I don't even want to think about it. But we now have every hydrogen possible. This is stearic acid, and this is the primary component in wax lips. No wax lips? No? Go find yourself some wax lips. I was hoping that crayons were made of stearic acid. They actually have some stearic acid in them, but mostly they're made of paraffin. Paraffin is a petroleum product that doesn't have the carboxylic acid. It is just at 18, 20, actually around 20, 24 carbons. And it's a wax. Crayons have some stearic acid in them, but a pure stearic acid crayon is actually a little bit too soft to work as a crayon, but I was hoping we could actually eat crayons, but nah, we ain't going to be able to do that. I mean, go ahead if you want. It's non-toxic, but you can't get any calories out of them. Now, stearic acid, it's a wax. And it softens at body temperature. It probably melts around 115, 120 degrees, so you could melt it and it wouldn't be all that hot. Candle wax melts at a higher temperature. Different waxes melt at different temperatures, like beeswax melts at a lower temperature than standard paraffin does. If you're into dripping wax on things, you don't even want to go there. There are some candles that when you drip the wax is damn hot, and then there are other candles that you can drip the wax, and the wax isn't nearly as hot, so choose wisely. Stearic acid would not be a particularly hot wax when you melt it. But, as we said, not all fatty acids are solid at room temperature. Wax lips are, but olive oil is not. What's the deal there? Well, I'll tell you. Remember, we talked about the fact that we can have carbon-carbon double bonds. We can have a carbon that has two bonds between it. And the carbon-carbon double bond essentially puts a kink. Now, you can't see it, but I just cut my leg up. So you can think of stearic acid being like this, all straight. And then when we put a double bond into it, it throws a kink into it. And so when you have these kinks, you can't pack the wax in as tightly. It's a little bit looser formation. Double bonds are going to lower the melting point. And that's actually a thing worth writing down on the board and you putting into your notes and remembering it. And that is this. Double bonds in a fatty acid will lower the melting point, i.e., the presence of double bonds will make this liquid at room temperature. So, here, we'll spin back. Now, let's throw a double bond into here. In fact, let's put in two. We're going to put a double bond. Here, I'll try my colored marker to see how that works. We'll put a double bond right here. Yeah, you can see that. And we'll throw another double bond over here. All right, now, if you're eating omega-3 fatty acids, the omega-3 refers to the fact that you have a double bond at carbon-3, and carbon-1 is the carboxylic acid carbon. So all an omega-3 fatty acid is a fatty acid that's got a double bond at the third carbon between carbon-3 and carbon-4 coming this way. So there's all kinds of tons of nomenclature. We don't need to worry about that. The main thing is we have these double bonds. Now let's look at this for a second. When we're talking about the double bond here, all of a sudden putting in a double bond throws too many bonds on this carbon. And so we're going to have to lose a hydrogen from each one of these guys. And so we've got a different little configuration there where we've lost the carbon. Now, we can also do this, where we have the hydrogens on opposite sides get removed. And this isn't arbitrary, and these two configurations have very specific terms. And let's just think about this for a second. When you got a single bond, the carbons actually can swivel around each other. But when you put a double bond, they can't swivel. And so the orientation of those hydrogens is fixed in space, and it can't be actually rearranged. So you can't go from both having them on the both side or having them on opposite sides. You can't flop it. They're fixed. Now, we have, of course, terms for these two different orientations. When they're on the same side, this is known as the cis configuration. And I always think cis, same side. When they're on opposite sides, this is known as the trans configuration. Now, I will just tell you that in living systems, biological systems, there ain't no trans double bonds. All double bonds in living fatty acids from living systems are going to be in the cis configuration. That's just the way we do it. Don't ask me. Well, go ahead, ask me. It's all cis. And we actually can't recognize to break down trans fatty acids, trans double bonds. So this leads us into an interesting story that is a brilliant story, not so much relevant now because trans fatty acids just are not part of our diet anymore, but it is part of the story of thinking about these things. We break down fatty acids starting from this end, not the carboxylic acid end, 2 carbons at a time. You're going to just pop them off, 2, 2, 2. And when you get to a trans double bond, the metabolic systems in the body look at that and go, what the hell is that? And you can't break it down, and it begins to accumulate in your liver. It starts to accumulate in the blood vessels, and it leads to hardening and narrowing of the arteries, cardiovascular disease. So trans fatty acids, not so good for you. But here is an interesting story. So imagine now having a piece of toast and putting a liquid oil on it. People do it, but it's not like the standard way. What you like is to have something like butter that you can spread on there. Now, ideally, you want the butter to be a little bit warm, and so it spreads very smoothly. Ooh. And butter, because it comes from cows, butter has got a composition such that it melts at body temperature. And you can think about this, is that the poor cows, if they were having crayons coming out of their teats, it'd be very painful. So the cow is at, I don't know what cow body temperature is. I ain't never seen a cow run a fever. I don't know, but probably about 100 degrees Fahrenheit, more or less our body temperature. That means that the fats in butter are liquid right at that body temperature. And then they will begin to solidify at moderate room temperature. And so they tend to melt in the mouth, not in your hand. All right, so that's why having the appropriate double bond configuration just right, and you kind of mix these things, to have the melting temperature at body temperature is really wonderful for flavor, for mouthfeel, as they say, and it's an important thing. All right, so we got a lot of liquid oils that don't work as a toast spread. At the turn of the 20th century, a chemical industrial technology comes about that is known as hydrogenation. And what you can do is actually begin removing double bonds and adding hydrogen to these double bonds to hydrogenate it. And you can take a liquid oil that's got double bonds in it and remove those double bonds by this hydrogenation process. You basically take the oil, put it over a nickel or a palladium catalyst, heat it up and bubble hydrogen through it, and depending on how long you keep it there, you can take a liquid oil and turn it into complete stearic acid, or you can have a mix of partial hydrogenations. Now, one of the things that happens when you partially hydrogenate it is that the industrial process is not biochemical, and it ends up scrambling the double bonds. So you end up with a mix of both cis and trans double bonds, and ordinarily you don't eat trans double bonds. So partial hydrogenation is an industrial technology that, starting around in the 40s, during World War II, there was butter shortages, whatever, and it's a really clever idea. I mean, I definitely think this is smart, is you take an oil that you don't really have a really big market for, say like cottonseed oil. What do you grow cotton for? For fiber. But you can get an oil from it. It is considered kind of vulgar, but it's considered a trash oil. It doesn't have a really high smoke point, doesn't have much of a flavor. It's not used for much. But you can partially hydrogenate it and turn cottonseed oil into a semi-solid. Make it into margarine. What a great market now. And so you add a little salt, a little flavor, a little yellow color, bada bing, you have got synthetic butter. And the really wonderful thing, of course, is you can mix the different kinds of oil compositions to give you the perfect melting point, such that it is going to be solid, but not so solid and hard that out of the refrigerator it won't spread on your toast. Because we all know there's nothing more tragic than trying to fix your peanut butter and jelly sandwich and getting butter straight from the refrigerator. It's cold and you tear your bread. Oh, no. In fact, one of life's greatest luxuries is to have softened butter. Ooh, I can get into trouble with good bread and softened butter. Margarine, though, comes from the refrigerator. It's got the perfect mix. It spreads out just beautifully onto your bread right out of the fridge. I love it. Margarine is also not going to be particularly perishable, because ain't nobody eating it, because you don't get it either. And we can get a lot of calories from it, but you can't get everything out of it, and you end up with these trans double bond bits, these fragments, starting to clog things up. Well, margarine was quite the darling of the food set back in the 40s and 50s. Apparently, during the Korean War, surgeons were observing that, doctors were seeing that there were young men, young soldiers, that were beginning to show signs of atherosclerosis, or narrowing of their arteries, and they actually began to make the association that is because the consumption of these trans fats, these partially hydrogenated fats. So that's 1950s. It only takes about 55 years for the authority, whatever, the USDA, to recognize trans fats really ain't all that good for us. And so around, probably 2008, 2009, we actually began to see a prohibition on the use of partial hydrogenation. And it took a while for various food agencies, different bakery things and restaurant chains, to be able to figure out how to make like the Popeyes biscuit without using partial hydrogenated fats, things like Crisco. And so starting around 05, 06, the tropical seed oil business began to really blow up because tropical seeds, coconut oil, palm kernel oil, these guys are growing in fairly warm environments, and so they tend to have a lot of saturated fats. And they can serve as a substitute for partially hydrogenated cottonseed oil and partially hydrogenated soybean oil. And so we now also have fully hydrogenated cottonseed oil and fully hydrogenated soybean oil, in which you're taking liquid oils, turning it into stearic acid, and then blending it with other oils, and you can make something that's got a bit more of a creamy consistency. And that's what our cream filling is in, I'm just looking over longingly at my little Debbies, I'm out of them. The cream filling is a partially hydrogenated mix. Now, it used to be it was partially hydrogenated cottonseed oil. Now it's palm kernel oil and totally hydrogenated cottonseed oil and stuff like that. So we don't have much in the way of partial hydrogenation anymore. That is just not a technology that's being used. But it was a clever way of using oils that otherwise would go to waste just because it causes heart disease. Really shouldn't stop the industry. Come on now. Margarine is perfect for spreading on your bread. No, don't. Eat butter. Just eat it. Or don't. But don't be eating margarine, please. No. Margarine is just an oddball thing these days. It is now primarily tropical seed oils and mixes of totally hydrogenated oils. All right, so now, how long have I been gassing on? A few more minutes here. So that is the fatty acid story. Pretty much all 18 carbon, and you have the cis double bonds, and let's stay away from the trans double bonds. The trans double bonds, right there. All right, let's make some fat polymers though, and it's not quite a polymer, but it's as close as we get with fats. In that, this is a free fatty acid, but that's not how fats are typically found. In plants and in plant oils, you can have a mix of free fatty acids and fatty acids that are kind of linked together. In animals, pretty much we don't have a lot of free fatty acids floating around. Most of our fatty acids are complexed up on a 3-carbon scaffold, a molecule called glycerin. And it looks like this, or glycerol. It's 3 carbons, 1, 2, 3, and it has OH groups coming off of it, like so. So this is glycerin, and it is a very viscous, slightly sweet molecule. Glycerin is found in a lot of baked goods. Glycerin is also part of lots of different cosmetics. And it's kind of a thick, gooey, sticky syrup. All right, what we're going to do is add a fatty acid to one of the carbons in the glycerin. And this is where the notion of a condensation reaction comes in, because I'm not going to bother drawing the entire fatty acid, but we're going to take the carboxylic acid end. Remember, that's the double bond oxygen and the OH. And then we just draw it like a line. That's the rest of the fatty acid tail. We're going to link this together, and to do so, we're going to make a molecule of water, H2O. So what we're going to do is pull off one oxygen and the 2 hydrogens to make this condensation reaction, and bada-da-bing, we have linked now this fatty acid to this glycerin molecule. And we have made what is known as, at this point, a monoglyceride. Now, if we add a carbon chain, a fatty acid here, we make a diglyceride. And you guessed it, if we add a third, we make a triglyceride. Now, as you get older, which God willing you will, and you start having blood work done, they're going to start giving you your cholesterol number. Cholesterol is a sterol, which is actually not a fatty acid. It's the basis for lots of hormones, but it's still a nonpolar molecule. They give you your cholesterol numbers, and then they give you your triglyceride numbers. Triglycerides are how fats are being circulated in the body, in the bloodstream. Triglycerides are what make up marbling, the white blubber, the white parts of steaks and your chicken fat. It's mostly triglycerides. You can find mono and diglycerides floating around in bodies that industrially ADM will purify for you and give you a railroad car full of monoglyceride, diglyceride, and triglyceride, separate them out in little tanks. And by mixing these, you can actually create some of these textures that commercially baked goods have by using mono and diglycerides. And in fact, if you recall, on our label reading, we were looking and we saw mono and diglycerides in there. So that is the way we can begin linking these fats into kind of a polymer. Now, the last part of what we want to talk about, though, is a very specific kind of diglyceride. And this is a really interesting fat, or interesting member of the fat category. Let's take this fatty acid and pull it off. And instead of putting a fatty acid here, let's put a phosphate molecule. And what did you just say? Negative charge. Now let's think about this for a moment. We have created a pretty bizarre molecule. We got this massive fat tail here, and we got this real negative charge here. Now, when this molecule is actually forming, that phosphate's going to spin up and rotate around, and we diagram it like this. The phosphate head and then the twin fatty acid tail. With a phosphate, this becomes a very special kind of fat known as a phospholipid. Phospholipids are the components of cell membranes. Now, if you want to know what phospholipid looks like, crack open an egg and eyeball the yolk. That's phospholipid. And most phospholipids, in addition to having a phosphate, they'll have a decorative molecule. It's a molecule called choline is the most common one. And this molecule, this phospholipid, in the food biz, so in the biochem biz, it's called phospholipid. But in the food biz, it's called lecithin. Lecithin is phosphatidylcholine, is what we would call it in the biochem biz. It is a phosphate group with a choline decorative cap, and it is egg yolk. So, some interesting things happen when we add this phosphate and begin mixing this with water. And let's look what happens. So we've got this really big fatty acid tail and then this really polar head. Some interesting things happen when we mix this with water. Let's group to this for just a second. What we got is a polar head and an extremely nonpolar tail. A molecule like this that is sort of schizophrenic with a polar head and a nonpolar tail, this is known in the biz as being amphipathic. And amphipathic molecules have some very interesting characteristics, to wit. If you mix an amphipathic molecule in water, watch what happens. We got water floating around here, very polar. And then we mix in egg yolk. So you can actually just do this as a thought experiment. Take an egg, and the yolk is all phosphatidylcholine, all lecithin. It's all this phospholipid. The white is pretty much all watery protein. And whisk it up. Now, I don't know the last time you made a scrambled egg, but you probably can imagine. If you take olive oil, which is just short chain, just fatty acids, and mix it with water and whisk it up, what happens? You can shake it, but very quickly the oil and water separate. Oil floats to the top, water goes down to the bottom. That's because oil and water don't mix. Polar and nonpolar interaction going on there. But if you take an egg and whisk it up and let it sit, now you probably shouldn't let it sit too long because it's not safe, but it won't separate. It doesn't separate out into a yolk and white. Once you scramble it up, you can't unscramble it. And that's because the phospholipid interacts with the water like so. We have the polar heads sticking out, interacting with the water, and then the nonpolar tails are sticking in, having their own little fat party. And we can create a little phospholipid blob. It's known as a micelle. Not your cell, it's my cell. M-I-C-E-L-L-E. M-I-C-K-E-Y. It's known as a micelle. And some really cool things happen when you're using an amphipathic molecule and you form a micelle. Because you can take egg yolk, whisk it up, and then begin drizzling in a little bit of oil. And the oil can get trapped in this fatty acid tail. So here's the oil getting caught. What we've made is a stable mix of oil and water. And a stable mix of a polar and nonpolar solution is known as an emulsion. And in order to make an emulsion, you have to have an amphipathic emulsifier. There are all kinds of emulsions floating around. Paints often have emulsifiers. One of my favorite things, not everybody's, but one of my favorite things is mayonnaise. We have made mayonnaise. You take egg yolk, you mix it with lemon juice, and then you begin putting in olive oil or any kind of oil to it. And one of the things to think about with this is that if you've ever made mayonnaise, it's actually a lot of fun. And there's some important parameters when you're making this. And I've explored this in my tartar sauce explorations. I love tartar sauce. Really the only reason I eat fish is because of tartar sauce. So you take mayonnaise and you add, chopped pickle, a bit of chopped onion, or chopped shallot, some pepper, whatever herbs you got growing in the garden, mix it all up. Now what I like to do is make it a little bit richer by adding a touch of olive oil. And I also add lemon juice. Now, when you're playing with your mayonnaise, you can start adding polar molecules like water or lemon juice, and it just starts to thin it out. It still stays white, no problem. It just thins and thins and thins and thins and thins. But if you add oil to it, you got to mix it up. And there's a limit to how much oil you can add to this thing. In fact, there's what's known as an aioli sauce, which is a really oily mayonnaise. Ooh, dipping your French fries in that, man, sorry, that's really good. And when you're putting in oil, that's what I usually do with my tartar sauce, is I add lemon juice, thin it out, and then I begin adding a little bit of olive oil back to it. If you add too much oil, you can break the emulsion. What happens is there's not enough fatty acids to hold that amount of oil, and you can recover by cracking another egg in there and whisking it up or adding more mayonnaise. So this is a classic sort of emulsified sauce. Ooh. And egg yolk is our number one emulsifier. Butter can act as a little bit of an emulsifier, but not as well. And so when you're at the grocery store checking out your various kinds of salad dressings, and you'll see the bottles, and you'll see some salad dressings have separated. And you've got the oil and the vinegar or whatever, and then usually at the interface is all the spices and stuff. And you shake it up, and it'll separate back out. Those are not emulsified. Then you have your emulsified guys, your Thousand Islands, your ranches, blah, blah, blah. Now, what I find to be a cheat is there are emulsified Italian dressings. And they're emulsified actually sometimes with phospholipid, other times with different kinds of gums, but they still are going to maintain a homogeneous column. Now, at like a salad bar, it's probably important that you have an emulsified Italian dressing, because it wouldn't work to dunk that spoon thing, what do they call it? A ladle, into there and not have a even homogeneous mix in that column of salad dressing, of Italian dressing. So the salad bar will often have an emulsified Italian dressing, but then they'll always have like the little cruets of olive oil and vinegar. So that is your emulsified dressings and such. I love mayonnaise. Now, while we're here with mayonnaise, what we've also driven over is the actual mechanism behind soap. Soaps are always amphipathic molecules. And when you're talking soap, it's got to be an amphipathic molecule in order to work. The number one soap, so check your shampoo, check any kind of soap that's got labels on it. The active ingredient is going to be something known as sodium lauryl sulfate. Now, Laurel is the organic chemistry term for 12 carbon. In the lab here, we just referred to it by the good old-fashioned dodecyl. Sodium dodecyl sulfate, also known as SDS. It is the detergent of choice in the lab. Sodium lauryl sulfate is the detergent of choice in your shampoo, your dishwashing detergent, your clothes washing detergent, your car wash, your toothpaste. Unless you're spending money to buy some sort of shishi-ass soap, you're using sodium lauryl sulfate. Now, different companies will say, oh, it's lauryl sulfate free. And what they'll do is, rather than having a 12-carbon chain, they'll put a double bond in it, and it's called sodium laureth sulfate. It's the same thing, whatever. Sodium lauryl sulfate is a pretty strong soap. You can make weaker soaps by shortening that carbon chain, and then it don't work as well. Now, here's how soap works. Sodium lauryl sulfate has got a sulfate head, which has got a pretty good negative charge, not quite as good as phosphate, but not bad, and then a 12-carbon tail. This is an amphipathic molecule. It's an emulsifier. And if you think about this, you get dirty because we have oils on our skin, and it traps dirt and bacteria. If things are completely dry and non-greasy, it's just dust. You blow it off. Your plates, your dishes. If you're eating something that doesn't have any fat in it, you rinse it rinses off, it's clean. But if you've got fats in your food, and of course we should be eating our fats, the stuff gets trapped in those fats. And unless you get rid of that oil, you can't get rid of the dirt. Your dishes won't get squeaky clean. So what do? You put a little squirt of soap on there. The fats get trapped in the 12 carbons. The sulfate interacts with the water, whoosh, wash it down the drain. That's why soap and mayonnaise are basically the same thing. And you may have heard about people using egg yolk or mayonnaise to wash in their hair. Make sure you wash it out really well. It smells pretty funny. That's the basis of it, because it is working as an amphipathic molecule. So we've got fatty acids They can be complexed up into mono, di, and triglycerides. There is the very special diglyceride known as the phospholipid. And just as a little point, phospholipids are the key to the membrane structure of cells. And they form like this, where you've got the phosphate head sticking out, and then the fatty acid tail sticking in, and you form what is known in the business as the phospholipid bilayer. And this is what the cell membrane is made up of. So the cell, if you crack it apart, the cytoplasm is very watery, aqueous, and the external environment is very watery. Think about blood, red blood cell. And so the phospholipid works because the polar part is facing the two watery parts, and then you got this little fat party going on here. And this actually is a critical part to how life works, because the phospholipid bilayer, this membrane bilayer, is able to kind of keep stuff outside or maintain stuff and keep it inside. It's a part of the compartmentalization in cells. And that is the main thing we have to say about fats. Just a few last bits. There is a non-caloric fat that's been on the market for a while. It goes by the trade name of either Olein or Olestra. Olestra is a synthetic fat, and that what they do is they have a triglyceride, but the fatty acid chain is not attached through a oxygen. It's actually got a little glucose molecule stuck in between, and it's attached to the glucose. And what that does is it makes it so you can't pull those fatty acids off of the triglyceride chain. And if you can't pull them off, you can't metabolize them, you can't break them down and eat them or consume them. They just go whoosh right out through the intestinal tract. Now, one of the issues is a classic laxative is mineral oil. So you consume a little dose of mineral oil, and it's going to just serve as a giant slip and slide for your colon, because you can't break it down at all. It goes straight through and whoosh, out you slide. Now, Olestra does the same thing. And so one of the things they had to put on the label, and I think they've been able to change the label lately, is that it causes loose stools, diarrhea, and something they called anal leakage, which I saw that on a label of Pringles, and I'm like, nah, I really am not interested in eating that. Olestra has not made quite the splash that they had hoped for it to. Splash may not be the best term, because it does cause some intestinal difficulties. As long as you don't eat too much, yeah, it's a good way of monitoring how much chips you eat. So it's an interesting notion, but it really hasn't taken off very well. We're going to stop here. We'll pick up on proteins and see where we go, and that's all I have to say. Thanks for your attention, and now back to your regularly scheduled program.